Well, hi everyone, and greetings from Northern Michigan. This is Bob the Science Guy. From time to time, I run into short subjects that I'd like to address eventually in a video, but never really kind of get fleshed out to cover an entire video. But they're relatively important concepts, so I thought today what we would do is I'd sit down and I'd have a little chat with you, and I'd go over a number of these and see if we could just get a few things cleared up. So let's cue up the music and get going. Well, the first subject that I'd like to cover is, does volume require a container? And this is related to, does pressure require a container? But we'll do it with volume first. This is a picture of the lake behind my house. There's the little island that they shoot the fireworks off of. Now, if you look there in yellow, you'll see I outlined an area that is approximately 400 by 400 feet, commonly known as 1 acre. Now that line on the surface of a lake is not any sort of a container. It's just an area of the lake. Now my lake is approximately 65 acres in size. That is one of the acres in my lake. Now I think that you will agree that that square contains a volume of water. It's from the surface down to the bottom of the lake, and it does not have any sides on it. It's simply an outline on a map. In other words, that line does not represent walls or any sort of a container. The only thing that's containing it is the bottom of the lake. Now, the pressure of the water at the surface or at any specific depth below the surface in that acre and in any other part of the lake is exactly the same. Water that's 1 foot under the surface there has got the exact same pressure as water 1 foot under the surface on the other end of the lake. That pressure isn't pushing on any particular surface. It's just the water pressure. Now here's the thing that I want to think about, and that is, does a volume require a container? Well, no it doesn't, and here's a good example of why. Now if I go down to the dam and I put another board in it, the water level in the lake will raise by 1 foot, and I will be adding 1 acre foot of water to the water that's in that square. Again, I've not added any sort of a container to it, but I have increased the volume of the water that's outlined by that square. Likewise, if I were to extend that square 400 feet off the surface of the lake and make it large cube, that cube would contain a volume of air, even though there are no walls on that volume. And that volume of air will have a mass and it will have a weight. The bottom line on this is, when it comes to water or air or land or anything else, if you discuss a volume of something, you do not imply or require that that volume be in any sort of a container. That seems to cause some people some problems, and I just wanted to explain it in a real-life example so that people could clearly grasp what I'm talking about when I talk about volume. Now, the atmosphere has a known pressure and temperature gradient. That's by definition, and it's not subject to debate. Here's an example. The pressure at sea level is a little over 1,000 millibars, and at 50 kilometers above the surface, that pressure has dropped almost to zero. This is how airplane altimeters work, and this is why climbers on Mount Everest require oxygen. The higher you go in the atmosphere, the thinner and the lower the pressure the air becomes. The reason that I'm mentioning this is that we need to talk about the second law of thermodynamics and the atmosphere of Earth. So let's grab a piece of paper and a pen, and I'll take you through it. Now we talk about something called the second law of thermodynamics and something called entropy. Now the rule is that entropy must always increase. So let's look at this situation. Let's say that we have 2 containers filled with gas, and they're connected by this pipe that has 2 things on it. It has a valve and it has a pump. Now, if this valve starts off closed and the pressure, P1, is much larger than the pressure of P2, for example, if P2 is a vacuum, and we open this valve, we all know what will happen. Pressure from the higher pressure area will rush through into the lower pressure area in this direction spontaneously. And it will continue to move until P1 equals P2. In other words, the pressure here equalizes with the pressure here. So this would be the spontaneous direction of movement of air. However, can we make air move back this way? Can we reverse entropy? As it turns out, we can. We can put a pump on this pipe and have a plug going to the pump. Well, if we don't plug this plug in, nothing's going to happen. The air will equalize through between both containers and it will not flow backwards against entropy. Because if we moved it backwards and created high pressure here and low pressure here, that would decrease entropy, and entropy must always increase. We can, however, decrease the local entropy in this system if we increase the entropy in the surrounding system. And here's how we'll do that. Let's go down here and we're going to get a power plant and we're going to burn coal, massively increasing the entropy of the coal. That is going to generate heat, which will boil water to steam, and then we will use the steam in a turbine and create electricity. And plug this plug into that electricity. So we're massively increasing entropy here, so we can actually reduce entropy here. So by turning on this pump, we can pull all of the air out of that container and put it back in this container in the reverse direction to the spontaneous process, and we can create a vacuum again and high pressure. Now let's have a quick look at another possibility. Say we have a very heavy-duty motor right here. And this is a big electric motor, and it's powered by a coal-burning power plant that has a great deal of increase in entropy because the coal is being burned. Now, once again, we have our two containers with P1 and P2. They're connected by strong girders and a pipe, an open pipe. Now, at rest, P1 equals P2 because thermodynamics and entropy demands that these two pressures equalize. However, the reason that this is a motor, and we have a very large weight out here, is that this is a centrifuge. We're going to start spinning this centrifuge very, very rapidly, creating a great deal of centrifugal force in that direction. Now, once this spins up, what you're going to find with centrifugal force, what you're going to find is that P1 will be greater than P2 because the mass of the air in these two chambers will be affected by this centrifugal force, and work will be done on the system in that direction. Work is defined as the displacement of mass in the direction of an applied force. So the air here has mass. We are applying a force in this direction. That air will move through this pipe from this chamber to that chamber. The result is that the pressure in the far chamber will be higher than the pressure in the near chamber. Now, we don't normally do this with gas, although we can use gas centrifuges. Many times in the lab, this is how we separate the cells from the plasma of the blood. With centrifugal force here, and with a pump powered by electricity here, we are performing work on the mass of the gas and displacing that mass in the direction of the force that we are applying to it. Now, you may have heard of something called the Second Law of Thermodynamics. The Second Law of Thermodynamics states that when you put an ideal gas into a container, that gas will expand to fill all of the available space. The pressure will be equal at any point in this volume, and the temperature will be equal at any point in this volume. Why is that? Well, we have nothing going into this system that will increase the temperature, and we have no forces acting on this container to change the pressure or create a pressure gradient. If, on the other hand, we have a pressure gradient where we have high pressure in one part of the container and low pressure in another part of the container, the only way that that can occur is if you have some sort of a force acting on the container that would perform work on this uniform pressure and cause a pressure gradient in the same direction as the force. Now, one thing that you will hear in the science denial community is that you have to have gas pressure before you can have a pressure gradient. Or if you bring up the pressure gradient to them, they're going to say, well, you're going to need gas pressure first for that. Let's see what they're implying with that. They're implying that we have a unified pressure and temperature to start with, and then if we open that container up and release it, it will expand in all directions. Because that's what the second law of thermodynamics, at least as they understand it, says it must do. But here's the problem that you run into. We have a pressure gradient in our atmosphere. So, tell me exactly what happens here to make this become this. And the next question is what needs to happen before this becomes this again. Now there's one more question that we have to ask. The science denial community likes to say that if we have pressure, there is a necessary antecedent that there be a container. So, what has to be done before all of the gas inside of that container has the same pressure and temperature? Because it would have to equalize within the container. Now, there's two other things that I'd like to mention on this. First of all, if they claim that you have gas pressure before you have a pressure gradient, at what time and under what conditions did you have uniform gas pressure before a gradient formed? They have presented absolutely no evidence for that. What caused that homogeneous system to spontaneously form a pressure gradient? And why, if we have a pressure gradient now, does the gas not disperse in all directions, or if it is contained within a container, form a unified pressure and a unified temperature? What are these conditions that were required to do that? They haven't answered any of those questions. If the second law of thermodynamics was acting on an ideal gas in our atmosphere, one of two things would happen. First of all, that gas would disperse into the universe, and we would have no gas pressure. And if there was a container over the Earth, that gas would expand to fill the available space, and we would have a uniform pressure and temperature throughout the atmosphere. We don't see either of those situations. What we do see is this, a pressure gradient. which mandates that there is an external force acting on the mass of the gas in our atmosphere. You cannot have a pressure gradient in a thermodynamically isolated system. You have to have that external force. So in reality, while it's true that gravity causes the pressure gradient within our atmosphere, more importantly, the fact that there is a pressure gradient in our atmosphere mandates the existence of a downward force, which we call gravity. Because if there wasn't a force of gravity, the gas pressure would expand outward to fill the available space, which is, I guess, the entire universe, and we wouldn't have any gas pressure or atmospheric pressure on Earth. Or, if there was a dome or container of some sort, it would equalize the pressure throughout that container. Unfortunately, those in the science denial community did not think their claims through, for they outlined this perfect proof of the existence of gravity and the absence of a containing dome. So this is Bob the Science Guy signing out from Northern Michigan. Thank you again for stopping by. Make sure you hit that like and subscribe, and I'll see you again soon.
Mama, please make them hear me. I can't teach them anymore. This rabbit hole's too deep for me. Feel my brain getting real sore. Bob the Science Guy. Bob the Science Guy.